So, it is called MEEP. The text is readable? Yeah. Okay. So, I won't read through all of this, I will just working through this, we will also get an idea of how to, what are the steps in running an FDTD program. Okay. So, let us go to, so the first example they have is, for example, fields in a waveguide. Okay. So, imagine there is a waveguide, I want to send a wave through it. Very simple, we know in these cases we can even analytically calculate what the fields look like, but that is not our objective. Let us see what this simulation does. So, the first line over here is, so this is, as I mentioned, written in a language called scheme, which is a slightly unusual language. So, we will not get into syntax, but what is being set over here, this size 16, 8 no size, this is telling you the size of the computational domain. So, 16 units in x, 8 units in y, and no size in z means it is a 2D simulation. Okay, that is all that it means. Okay. Next, I have to make the object. What is the object? It is a waveguide. So, a waveguide as shown in this figure over here is this black strip over here. So, it is like a slab waveguide, right. So, I have x is along the waveguide and then y is the other axis, right. So, here the waveguide is being made. So, it is being made as a block of some epsilon. So, epsilon 12 has been given. Okay. The width is given as 1 unit and infinite in the other dimension. So, fairly intuitive, right. So, the width of this black strip is 1, it has epsilon equal to 12 and it extends forever. Okay. Of course, it does not extend forever because I have defined the computational domain above to have 16 units over here, right. So, in practice it is going to be 16 units, right. Now, by default everything else is vacuum, that is what you would expect. Okay. Next comes a source. I need to put a source to excite some field in the waveguide. How will I get a wave in there? So, what have they done? They have made a e to the j omega t kind of a field. Okay. They have given some frequency in normalized units 0.15, that is the frequency, and they are saying that it is Ez polarization over here, and they have given some center for it. Okay. So, center, remember our size was 16, so minus 8 to 8. So, at minus 7, that is at the almost at the leftmost part, I am putting a Ez polarized source. And what kind of a source? Continuous wave. It is not a source that starts in time and then decays in time, it is a continuous wave. Okay. The dielectric is the waveguide. This black strip over here is the waveguide. Why won't the wave go out? Okay, good question. Why won't the wave go out? So, I am exciting it within this. I mean, so this is something which you should have studied in your undergraduate course. Huh. No, so the field does leak out. It is not the case that the field is strictly confined within the dielectric. The field does leak out. In fact, we will see it. Okay. It is not confined purely inside. Some of it does leak out. We do not have to worry about how much is undergoing TI or total internal reflection. The Maxwell's equations will take care of it. Yeah. Some will be guided, some will leak out. Okay. So, we have specified the source. What else do we need to specify? Boundary conditions, right. If I do not specify boundary conditions, my simulation will be wrong. So, they have specified here PML. This is just one line specification. Set a PML of thickness 1. So, by default what it will do? You look at this computational domain over here, it will put like a picture frame of thickness 1 all around. Okay. That is why the source was put at minus 7, not at minus 8, because you do not want the source in the absorbing material, you want it just outside. Okay. So, the PML is from minus 8 to minus 7 and the source is at minus 7. Okay. Now, remember your delta x and delta t is yet to be specified, right. So, here we set, for example, this set resolution. So, that is setting delta x in some normalized way. Okay. The Courant parameter is a default parameter that is already fixed in the simulation. You can change it if you want, but they give you a default which will be a stable number. So, fixing delta x is good enough, delta t will get fixed according to the Courant. Okay. Then finally, you have to tell the simulation that how long do I want it to run. So, you say okay 200 time units, some more commands are given to output the fields and all of those things. Okay. This is what the output of the simulation is at the end of 200 seconds. This is what the fields look like, right. So, the source was over here, and looking at this, can you say that there is definitely a waveguiding happening? Clearly, right, the field is very nicely confined to the waveguide, but not strictly. Some of it is leaking out, no problem, right. It's not, and this is not a lossy material. It's just epsilon equal to 12, there is no imaginary part. So, this field will go on for a very long time and distance, right, but you can see it's leaking out. Next to the left hand side interface, you can see there is something strange happening over here. That is because there is a PML over here. So, it is absorbing it almost perfectly, but I mean in practice some of it will not get right. Right. So, they make a point here that because they turned on the field abruptly, right, the simulation started at t is equal to 0, and the next instance there was a e to the j omega t term. So, we know that as far as physics is concerned, there is an abrupt turn on the field. So, there will be some high frequency components, right. So, that is what they say. Towards the right hand side over here, the field looks a little what they call speckled. You can see the field over here, it has some, the shading is slightly different from at the very beginning. Here it is a nice homogeneous dark red, here there are little white dots inside the red. So, that they say is coming from the high frequency components that came as a result of turning the field on abruptly. Good question. What is the red and blue? So, red will correspond to maximum positive, blue will correspond to maximum negative, right. So, it's like a wave that is traveling, right. So, alternate maxima and minima in a wave, that is what is happening. The thing in the, white is 0, white is 0. So, that is what they call this dark blue red, that is the, you specify the legend for the color. So, that is how they do it. So, typically when you see a simulation of red and white, then you should assume that one is maximum positive, one is maximum negative, and white is 0. This dot, that is the source. The dark thing actually that's like the darkest red, and this is the darkest blue. That is all. I mean, they are just shades of blue and shades of, not blue and red, shades of dark blue and dark red. So, dark blue red is one legend, blue red is another legend, you can choose. Okay. So, people use different things for enhancing the contrast. Okay. So, this is an example which you could have done analytically also, right, but the power of FDTD is that you can do things which are analytically not possible. So, for example, they consider a 90-degree bend in the waveguide, which would not be possible to solve analytically, right. Now, what do you expect physically to happen? I take a waveguide, it's guiding a wave, I bend it by 90 degrees. What do you expect will happen physically? Some of it will leak, it's not like a pipe of water that I bend it and all the water goes out. Some of it will leak out, that is what we expect. So, let us see what if our intuition is confirmed over here. Now, same thing, they say make the computational domain as before 1616, and you have to make 2 blocks, one like this and one the 90-degree bend. So, they have shown it over here. So, one this way, and they have done it by specifying 2 blocks, same material, but just the coordinates are different. Okay. PML resolution, everything as before. Okay. Now, to avoid that speckle phenomena, what are they doing? Instead of turning the source on abruptly, they are making it no, they are still using a what are they doing? Continuous source wavelength, okay, width so much. Yeah. So, what they are doing now is here they say instead of turning the source on suddenly at t is equal to 0, we ramp it slowly over a time proportional to the width of 20 time units. So, this width equal to 20 time units is giving you the turn on time of the source, okay, and the wavelength is given to you over here. Yeah. So, technically MEEP is implementing this turn on function using a tan hyperbolic function. Okay. And as I mentioned, this is open source. You can go and look at their code and see how they are implementing it. Okay. And as before, run it for 200 time units. So, let us see what the output looks like. Here is what the output looks like. So, yeah, this you can see this is a animation. At every time instant, you can record the field. So, you can see the field is going, now it hits the bend and it begins to come into the lower part of the bend, but most of it is getting leaked out at that interface. Okay. So, that is another very cool aspect of FDTD. If I store the EZ at every time instant, I can put it all together and make a GIF file. So, what they are showing over here is a GIF file. You can see the animation. So, then you can optimize various parameters if you want to minimize the leakage and all of that. We will not go into that. Then the final example I want to show you is modes of a ring resonator. Okay. So, you all have heard the word resonator. It means that it is a structure which is selective in frequency, it allows some frequency and it disregards other frequencies. Now, supposing you want to design a resonator to work at some frequency, how will FDTD help us in that? Okay. So, okay. Let us look at the geometry over here. So, what have they done is they have made a ring resonator. Okay. So, what is a ring resonator? Take the waveguide from before, join it into a circle. Okay. So, we know that integer multiples of the distance around this are what will be the supported modes. Okay. So, we want to confirm that intuition over here now. So, they have the width of the waveguide, the radius, all of these are being specified. Yeah, some 2 pi r, but n lambda in the medium. Yeah. Okay. So, they are making a cylinder over here, all of this is what you would do to make the object. Okay. Now, question lies, what should if I excite this structure with the wrong frequency, what will happen? Nothing will happen, right? The field will not decay, the field will decay off, it will not be a resonant phenomenon. But once I have designed a structure with some epsilon, if the geometry is slightly complicated, I would not know what the resonant frequency is. So, how would I find that resonant frequency? I can, in FDTD, I can specify a source. Well, okay, after that what? Supposing my task, someone gives me a structure and says find out the resonant frequencies of the structure. Excite it with all frequencies, right? So, that is, well, all frequencies is technically impossible, wideband, right? So, the step 1 is excite it with a wideband. Okay. So, here they say they are making a pulse kind of a frequency. So, they are saying the center of the pulse is some 0.15 in normalized units and a DF, right. And like we have discussed earlier, they use a Gaussian source. So, they give a Gaussian source where they specify the center frequency and the width. Yeah, so they work, these are physicists, they work in a strange set of coordinate units where speed of light is 1. Okay, so everything gets normalized very nicely to 1, right. So, yeah, it takes a little getting used to, but once you get used to it, it is very powerful. Everything is normal, yeah, speed of light is 1, wavelength is 1. So, yeah, whatever. Then you run it for some time 300. Okay. So, now let us imagine we have done this simulation. How will you interpret the output? Output will be fields at all times and positions. Now, what? No, but we are exciting it with a wideband. But I am not getting frequency information in my FDTD's output is what? E as a function of space and time, there is no frequency. So, what do I have to do? That is a very, yeah, so he is saying go around the structure and find out where the nodes are. That is a very crude way. Is there a smarter way? Find out the Fourier transform. I have time domain data, calculate the Fourier transform. That is a much smarter way. It will give me not just the frequency peaks, but also how resonant they are, how sharp they are, right. So, these guys have an inbuilt function called harm inverse. This is, right. So, this is like the inverse Fourier transform. So, the simulation itself says that run your simulation for 300 time instance. At the end of it, after sources get over, run the inverse Fourier transform at this position, okay, and some center frequency is given to you, okay. So, again this is something that they have coded, okay, and output comes in text. So, you can see that when they do this, the peaks are extracted out. So, you get 1, 2, 3 peaks you get. So, that is the frequency, and the Q, the quality factor, right, that tells me, if you have studied this before, quality factor tells me how good the resonance is. So, the Q factor also comes out. So, for example, the first mode has a Q of 80, then 300 and then 1677. So, 1677 corresponds to the Q which lasts the longest, right. So, there is some theory of inverse Fourier transform, but you all know that, okay. And so, the next thing I could do is pick each one of those frequencies and rerun the simulation with a narrow band at those frequencies. That will excite only that mode and not the others, right. So, what they are showing here are those 3 modes. So, the first mode, the second mode and the third mode, okay, and these are again GIF files produced. So, this is, you can see this had the lowest Q, right. What were our Qs? 80, 316 and about 1600. So, this is the lowest Q, and that is, you can see that a lot of the field is leaking out, right, outside the waveguide, outside this resonator, a lot of the field is there. As the Q becomes larger and finally larger over here, here the field is much more strongly concentrated inside the resonator, right. So, I have made a structure and I am able to identify these are the resonant modes by using simple FDTD and inverse Fourier transform, signal processing. Okay. So, that is to sort of show you what should you say, in practice how would you use FDTD, and it is very powerful, design any structure, excite any fields, right, and they have lots of other solved examples for photonic crystals and other structures like that, and it is easiest to run it on a Linux machine. Okay. So, that brings to an end this demo also on FDTD.